All right, so good morning once again. To those of us who just joined, I welcome you to today's section for our fourth Meteorological Virtual Series. I'm Maureen Abla Anyataku, and then a senior meteorologist at the Ghana Meteorological Agency. I'm going to be your MC for this seminar. So for today, we will be having our presentation on the topic characterizing the environments of MC, that's Mesoscale, across West Africa and evaluating precipitation forecasts. And this presentation will be done by Mr. Michael Baidu. He's currently a Ph.D. candidate at the University of Leeds, that's Institute of Climate and Atmospheric Science, School of Earth Science in UK. He's a meteorologist, and in this presentation, he's going to take us through the introduction to climatology of the environment of mesoscales in the different sub-regions of West Africa and the type of storms associated with them. Then he will also let us understand the effect of shears on the intensity of mesoscales, and finally, an evaluation of the performance of Met's Office Tropical Africa model in West Africa. I know I've mentioned a lot of terminologies for those who are not meteorologists here, and that is why we are all here to learn. So our presenter will help us understand all these terminologies and appreciate the understanding of this presentation better. As we are all aware too, climate change is on the rise and we are having a lot of impacts where some areas are experiencing floods, some are experiencing droughts, some are experiencing even high temperatures, which is affecting livelihood. So at the end of the day, we are all going to understand these basics because these are the things that brings about this high impact weather within our sub-region. So without wasting time, I'll call on our presenter, Mr. Michael Baidu, to start the presentation for us. Thank you very much.
All right, yeah, thanks so much, Maureen, and thanks so much, all the organizers for giving me this great opportunity to share my work with you. I am trying to share my screen. I don't know if you can see it. Can you confirm that for me?
Yeah, your screen is seen. However, if you can make it bigger. Yeah, it's better now. Okay, cool. Yeah. All right, so just like Maureen was introducing me, my name is Michael Baidu. One thing that I just want to mention is that I did my first degree, my bachelor's degree, and my MPhil from KNUST, and I also worked with the Ghana Meteorological Agency before coming to start this PhD. So I believe that some of my professors who trained me from KNUST are probably on this call, and I see it as a great opportunity to share what I have, the research I'm doing with these people. Yeah, so I'm speaking on the topic characterizing the environment of MCSs across West Africa and evaluating precipitation forecasts. I am working currently with Julian, John, and Caroline Bain from the Met Office. They are my supervisors here in the University of Leeds. So just like you said, every term that you see here is going to be explained in the course of this presentation. So the introduction or the motivation for this work is that mesoscale convective systems, when we say mesoscale convective systems, they are the storms that you see here. So the image that you see here is a satellite image that was taken on the 1st of June 2020. It indicates some of these convective storms that affected West Africa. And then, so these storms are normally associated with very strong winds. And I'm sure that you've been experiencing them, strong winds, thunders, lightnings, and it's so it's one of the most devastating high impact weather systems in West Africa. And the main problem is that numerical weather prediction models struggle to represent these storms in the region. Because I mean, if you look at these systems, the initiation point of the storm regions are smaller than the great sizes of most global models. And so these are not directly resolved in global models. So they have to be parameterized. So it results in a lot of inaccuracies in the ability of the models to simulate the exact location
and the intensity of the convective system. So this has been a great forecasting challenge. And so a better understanding of the processes that influence the intensities of these systems is very, very crucial. And that is the focus, that is the motivation for this work. In the course of this presentation, there are three main research questions that are going to be addressed. And so the first one is, what is the climatology of the dynamic and thermodynamic conditions associated with MCSs in West Africa? And then the second one is, what is the effect of vertical wind shear on the intensities of MCSs? And then the third one, the last part, will be the performance, evaluating the performance of the high resolution Met-Office Tropical Africa model in West Africa. So the first question, so what is the climatology of the thermodynamic environment associated with these storms in the region? Very, very important in being able to predict them accurately. So to address this, we track MCSs. We use MCS data that were tracked from 1998 to 2007 from the Huang Eta algorithm that you will find in his paper. So the storms, the MCSs were tracked from Huang Eta's data. And then also we select the environments associated with the storms, the winds, the convergence, the temperatures, the different pressure levels were all selected. We obtained them from ERA interim, and then the associated rainfall was also obtained from TRIM. The plots that you see here is the number of MCSs that were tracked in the region over the period from 1998 to 2007. We have overlaid on this plot here the 925 hectopascal winds, or the surface winds, okay? And then also I have shown in contours the orography. So you have contours of about 400 meters above sea level, 800 meters above sea level. I've shown this orography. So what you see when you look at this is that you see that most of the storms are occurring around regions of high orography, and also are influenced by the surface, the near surface winds, which is the winds that mainly bring in the monsoon flow. So more MCSs generally affect the region. So we look at this for different seasons. Okay, so for DJF, December, January, February, March, April, May, June, July, August, and September, October, November. In DJF, most of the storms are concentrated over the ocean. So you have most of the storms over the Gulf at this time, because at this time the Sahel or West Africa is in the dry season, and the movement of the storm have been shown to follow the oscillation of the ITCZ. Literature has shown that most of the storms are located typically about 10 degrees southward of the ITCZ. So from March, April, May, as the ITD begins to move northward, you begin to have the convective storms moving along with it. So in March, April, May, you begin to have a lot of storms beginning to affect South West Africa. And also you begin to have the storms by June, July, August, they reach the Sahel, which is the northern part of West Africa. Then from September, October, November, as the ITD begins to retreat, you begin to have the storms also retreating along with it. One thing that is very important for you to notice as I move along is the location of the regions of study. So over here, I showed the study region was demarcated into 6 different sub-regions. So we separated the Congo region from the coast, Southern West Africa, Sahel, North Atlantic, and the Gulf. So in the course of the presentation, if you see any analysis over the Gulf, the Southern West Africa, Congo region, these are the regions that we are referring to. Okay, so the first thing that I show here is the climatology of the vertical profile along a storm, along the storm. So basically what we do here is that for each of the regions that we are studying, the Gulf, the North Atlantic coast, Congo, Sahel, and Southern West Africa, we take composites, we create composites of all the storms. So all the storms that affected the Gulf, all the storms that affected North Atlantic, we put all of them together, and then we study the environmental conditions associated. So we try to define the main environment associated with the storm. So what I am showing here is taking a vertical profile along the storm composites for each of these regions. When you look at this, the first thing that strikes you quickly is the fact that storms over the land are associated with higher Cape compared to storms over the ocean. So you see that storms over the land are like the Congos having higher Cape here, Southern Sahel, Southern West Africa. But when you compare to these oceanic storms, they are different. And also along it, I have also shown the winds, the strength of the winds associated with them. So you see that for the land storms, you have upper level winds, upper level easterlies associated with these land storms. You see the same, you see this in the Sahel, you see the same in Southern West Africa, and also in the middle, you have strong mid-level winds associated with the storms, which is also called the African easterly jets associated with the storm. You actually see that over the ocean, but you don't see these the same at the upper levels over the ocean. You see that over the ocean, you don't have that strong upper level winds over there. You only have these mid-level winds. That I want to mention is when you look here at the coast, you see that at the south, you have low-level southwesterlies, okay, low-level westerlies here. That seems to indicate the presence of a shear, okay, low-level shear in this region. And one key thing that I'm answering in this presentation is the effect of this low-level vertical wind shear on the type of storm that results in the region. Also printed on these plots, on these taphograms, are the associated rainfall values, mean rainfall values, mean rain rates associated with each of the regions there. And also below it is the speed, the mean speed of the storm in the regions. When you look at the mean rainfall rate, what you see is that the storms over the ocean have higher rainfall rates. So you have higher rainfall rates for the Gulf, for North Atlantic over the land. The rainfall rate is quite relatively low. So basically, the oceanic storms are associated with higher rainfall rates compared to storms over the land. It is amazing that even though land storms have higher Cape, they are not directly having higher rainfall rates. So that means that Cape is not necessarily a direct measure of how much rainfall you obtain from a storm, which is very important to know. The next thing that you also see is when you compare the speed of the storms, you realize that the land storms propagate faster. They have higher speed, 12 meters per second, 13.9 meters per second, as compared to the storms over the ocean. So you realize that the land storms propagate faster, even though they have lower rainfall, they propagate faster than the storms over the ocean. These are very important characteristics I want to take note of. The next thing that we have investigated here is the conditions, okay, 2 days before the storm arrival to 2 days after the storm arrival. Remember, we are studying composites of storms in the region. So we are looking at the environmental conditions. So what happens 2 days before an arrival of a storm to 2 days after? So what I have shown here in color is the divergence. So that blue indicates convergence, whilst red indicates divergence, okay? And then I have shown vertically through the storm. So you have on the y-axis the different pressure levels, and also when you look at the x-axis, you are seeing the conditions 2 days before the day the storm arrives. So if you look at where you have 0 is the day 0, and that is the day the storm arrived. And then when you you have minus 1 day, minus 2 days. So 2 days before the storm arrived, 2 days after the storm arrived for each of the regions, okay? And also overlaid is these dotted contours are the associated vertical velocities associated with these storms. That is the dotted contours. And also when you look at, the thick line that you see here is the rainfall associated with the storms. So that is shown on this second axis here. You realize that mainly storms over the oceans, you see that before the arrival of the storm, there is a strong surface convergence. Now, this strong surface convergence, okay, results in strong vertical velocities just before the arrival of the storms, and then which will be compensated by an upper level divergence added, okay, and you also have strong rainfall happening on the day of the storm arrival. This is actually but over what you see over the oceans. And then when you come to over the land, you see a very strong variability, especially, let me use Sahel, for instance. You realize that the strong convergence that precede the arrival of the storm actually happens, in this case, about 6 hours before the arrival of the storm. So you begin to already have a strong convergence happening. This is data from ERA interim, and the finest temporal resolution was 6 hours. So from about 6 hours before the storm arrival, you already begin to experience a strong winds at the surface, convergence at the surface that results in strong vertical velocities and associated upper level divergence. And then you have the associated rainfall happening. And then one interesting thing that happens after the arrival of the storm is this outflow, this divergence that you see here right after the storm. And that is basically indicative of an outflow from the storm. As the storm empties itself of rain, as it's emptying, you begin to see an outflow from the storm, which could be from cold pool or any kind of outflow from the storm after the storm arrival. And then the condition repeats itself the following day. One unique thing you see when you look at the Congo region is that the convergence associated with these storms here seem to be happening around 800 hectopascal or somewhere around 750 hectopascal. The convergence seems to actually start from levels and then it maximizes around these mid levels, and which we speculate that the presence of orography, high orography in the Congo region could be the reason why we have this kind of convergence happening here. It is interesting that when you look at the Sahel and Southern West Africa, you also see quite a similar thing. In Southern West Africa, you see the convergence happening about 6 hours before the storm arrival. You already begin to have a strong convergence. As you move forward in time, this convergence begins to get maximized around 800 hectopascal level. So this is one thing that most people have been speaking about. You have the convergence actually intensifies around this level, and then you have the associated rainfall. So of course, there's so much on this. So let me just move on and show how these conditions happen. So this time I'm looking at the environment horizontally. Okay, so if you look at it horizontally, where blue still indicates convergence and then red indicates divergence, and the mean storm location I've indicated with these green dots, and also I have overlaid in the yellow contours the presence of the African easterly jets, the 600 hectopascal winds. The black contours indicates relative vorticity associated with the storm. So if I focus now on the North Atlantic, what you see here is that the point where the storm is located happens to be south of the African East jet core. So you see that the mean storm location in this region is mostly south of the African East jet core, but it happens to be within a place of strong relative vorticity. So you see that the storms are mostly associated with the trough of the African East wave. The strong mid-level relative vorticity is an indication of the African East wave. And that is basically what you see in most of the regions. In the Sahel and Southern West Africa, one striking thing that you also identify is a large band of convergence located at the north of the storm location, which actually is an indication of the location of the ITD, okay? The position where you have the ITD, you have that strong band of convergence. So that is what you see at the north of the storm. So remember I mentioned that the storm is located about 10 degrees south of the ITD. When you look at this vertically, you also, the picture comes clearly where you have a strong convergence at the surface resulting in strong vertical velocities and then divergence at the upper level. Yeah, so this is basically the environment associated with the storm. So we move on to the first question we are addressing here. What is the effect of vertical wind shear on the intensities of storms? And I think that this is a very interesting part of the work that I need you to pay attention to. So to talk about the effect of vertical wind shear, I want to give a background, okay, of the association of the vertical wind shear with the storms in West Africa. So I show here a vertical transect along the longitude 0 degree in West Africa. What I've shown is the zonal wind. So blue means easterlies and then red indicates westerlies. So on the y-axis is the pressure levels and on the x-axis is the different latitudes. I have shown for the different months, January, I've shown for April, July, and October. The peak of the monsoon season is in July. So I wanted to focus on July because that is where you see the characteristics associated with most of the storms. In July, most of the storms, like I showed in the first plot, most of the storms are located between and in the Sahel mainly. That's what I'm in July. Most of the storms are in the north, in the Sahel. So between latitudes 10 to 20 degrees north, you have a lot of intense storms happening here. So when you look at this in July, you realize that the intense storms that we observe in the Sahel at the peak of the monsoon is associated with low-level westerlies and also strong mid-level easterlies, and that is the African East jet. So you see that the storm is associated with a strong vertical wind shear. And so it's very important to investigate how the vertical wind shear affects the storm intensity. So there are recent works from Chris Taylor, Connie Klein, that have found that an increase in the frequency of intense MCSs in recent years have been found to be associated with this strong increase in shear. A recent work has indicated that this, an idealized study has indicated that this may be happening by decreasing entrainment. So the strong shear is decreasing entrainment, and that is the reason why. However, even convection permitting climate models struggle to represent this effect. And the reason is because the exact mechanism through which shear affects affects MCSs have not been thoroughly understood. And that is the motivation of this part of the work. And so I just want to mention some few proposed theories. And the first one is the RKW theory. He explained the effect of shear mainly based on dynamics. So he said that a balance between the vorticity generated from a cold pool from the storms and that generated from shear is what results in the optimum situation that results in intense storm. A more recent work by Alfaro introduced a thermodynamic component of the effect of shear. And then what he did was to compare different, in his idealized study, he compared different amount of shear, okay, small shear and then large shear. And then he showed that a stronger shear results in an increase in the inflow of convectively unstable air into the storms. And this results in strong latent heatings, and that is why shear results in intense storm. In the current work, we focus on the effect of shear on the cloud heights of storms. So we refer to this work by Takahashi in 2012, who used CloudSat radar reflectivity data to compare the level, the cloud top height, with the level of neutral buoyancy obtained from sounding. So the level of neutral buoyancy obtained from sounding is supposed to be theoretically where you would expect the top of the clouds to be. But he realized that in reality, the level of mass outflow happens to be about 3 kilometers lower than the theoretical level where you would expect it to be. Okay, and the level of neutral buoyancy that is calculated from sounding, when you plot a tephogram, the level of neutral buoyancy, the parcel ascent in the tephogram is based on an adiabatic ascent of the parcel. When we say adiabatic, it means that the parcel is rising without interacting with its environment. And so if a parcel was to rise adiabatically, it was supposed to reach this level. But in real life, real storms interact with the environment. They do not rise adiabatically. And that is the reason. So real storms entrain air from the environment. So the key question that we address here is, does shear affects the cloud top heights of storms, or does shear affects the difference between this level of neutral buoyancy and the actual cloud top height? To answer the first question, we have plotted here the associated cloud top temperatures of storms, okay? And then overlay surface winds, the 925 hectopascal winds. And then in contour, I have shown the 600 hectopascal winds, okay? So what you see is that the region where you have the coldest of storm happens to be collocated with a region where you have the strongest shear. So we see that shear is associated with colder cloud tops. But how does this relate with their level of neutral buoyancy? So to address this, we define what we call the brightness temperature difference, which is the difference between the cloud top height temperature and the temperature at the level of neutral buoyancy. So that is what is plotted here on my left. And then plotted alongside it is the associated shear values. When you look at this brightness temperature difference plot, the key thing that strikes you first is the clear difference between the oceans and the land. You realize that storms over the oceans have a minimal brightness temperature difference, or storms over the oceans are more easily able to reach their level of neutral buoyancy compared to storms over the land, and which we speculate that entrainment of drier air into land storms is what prevents them from reaching their level of neutral buoyancy. Actually, recent works by Becker and Honegger proposed that they actually found that storms over the land have higher entrainment rates compared to storms over the ocean. And then a work by Peter et al. 2019 has indicated that actually the land storms, the drier air over land dilutes, results in the increase in the entrainment-driven dilution of the updraft core. So the updraft of the storms is diluted by this drier air, and that is what prevents them from reaching their level of neutral buoyancy. It is, however, amazing when you look over this region, the Sahel region, or the happens to be the region with a strong vertical shear. You see that brightness temperature difference is minimized in these regions. And so we see that shear, even though this is also a land storm, okay? So you see that shear minimizes the brightness temperature difference, which is an amazing thing that has been found in this work. And we also look at the effect of shear on other storm properties. And then we see, so we have plotted here on the y-axis the vertical wind shear on the x-axis, the speed of the storm for the different storm sizes, for the brightest temperatures, for the associated rainfall, and the lifetime of the storm. You see that large storms are associated with the increasing shear results in moderate sized storms. And also you realize here that increasing shear for moderate speed storms, for storms with speed greater than 10 meters, the increased shear results in colder storms and also results in higher rainfall rates and also results in longer lived storms. So a strong shear is resulting in longer lived storms, storms with higher rainfall rates, and storms that are colder. So the conclusion of this part of this work is that storms is shown here. The 2D histogram plot that I have here at the bottom here is just the representation of the effect of shear on brightest temperature statistically, okay? So I show that as the shear increases, the brightest temperature decreases clearly for all the storms over the land. So generally, storms over the oceans could reach their level of neutral buoyancies compared to storms over the land, which we speculate that entrainment of higher entrainment over land compared to the ocean is what prevents them from reaching their level of neutral buoyancies. And also the difference between the observed cloud top height and the level of neutral buoyancy is minimized over regions of strong vertical wind shear. So the key message, okay, the key finding from this particular part of the work is that a strong vertical wind shear results in higher cloud top heights relative to their level of neutral buoyancy, and which we hypothesize that it happens by increasing the updrafts and then minimizing entrainments. I move on to the last part of the work, and which is now we look at the performance of the Tropical African model, the high resolution Tropical African model from the Met Office. The motivation for this is, as mentioned earlier, is because forecasting MCSs in the tropic has been a major challenge because global model parameterized convection. When I say parameterized, if you look at the thing that I have here, which I obtained from my Met Office supervisor, Caroline Bain, it shows that you see that the great sizes of these, some of these storms happen to be smaller than the sizes of these storms happen to be smaller than the great sizes of global models. That means that these storms will not be resolved directly by global models. And so you have to represent these small sub-grayscale features. It's not just this, in this case, we are just showing this cloud, but so you can talk about orography, you talk about vegetation, all the sub-grayscale processes that are lower than the gray sizes of the storm have to be represented. So you can clearly see the effect of it on the forecast scale. You see that this storm here is just affecting a small fraction of the gray box here. But in parameterizing it, we have put the value over the whole grid box. So that means that in all the areas that are not supposed to be raining are going to be having rain. So then you realize that the global models are therefore going to have the storm spread along a very wide region, resulting in a lot of false alarms. And that's the reason for these inaccuracies. And that's the reason why a convection permitting model, a high resolution model, is important, so that we will be able to resolve these small scale features. And fortunately, the UK Met Office runs a high resolution model. And so it's important to evaluate the performance of this model, whether it is performing well or not. So I have here an example of the operational, the Met Office Tropical African model compared to the global model. So the first one you see here is the global model, and the second one is the Tropical African model, and then the last one is the observed GPM. Okay. So when you look at this, like I said, you see that the global model just puts the rain over the storms over it just fills the whole grid, but it just puts it everywhere. So it's kind of overestimates the sizes of the storm in this case because it's parameterizing the storms. Now, by using the high resolution model, the convection permitting tropical African model is trying to address the problem of the global model, but it ends up with storms of higher intensities and storms of smaller sizes than the observed. And so, and also one other interesting thing about this tropical African model is the spin-up problem. The tropical African model has a long spin-up period. Okay, so that means that it takes a long time for the model to reach equilibrium with reality. So once the storms are initialized at 6 o'clock, it has 12-hour spin-up. And then when it's initialized at 1800, it has 18-hour spin-up. So one thing that I want to alert forecasters about whenever you are making forecasts with the tropical African model is just be aware that it's affected by the spin-up problem. So if you are looking at a forecast within the first 12 hours or the first few hours, be aware that the tropical African model is not going to be that accurate in that case. Okay, so that is one thing that is very important. So it is mostly day 2 forecast is better than day 1 forecast. Now, to verify, the method that is used here is called a fractional scale score. And the reason why we do not use the point-to-point verification system is illustrated here. I obtained this illustration from Beth Woodhams, who possibly is on this call. So, like I said, if you consider the red to be observed and then the gray to be the forecast, the global model, if this is the gray size of the global model puts the storm everywhere. And so if you are doing a point-to-point verification system, then the global model is going to get because, I mean, the storm will just find itself within the location. But when it comes to the high resolution convection permitting model, you realize that the high resolution model has actually simulated a storm, but it has put it in the wrong location. Sometimes a small perturbation in the initial condition can result in these inaccuracies. And that's the reason why some people are looking at exploring ensemble system. So this has simulated a storm, but it has put it in the wrong location. So that means that if you do a point-to-point verification, you're going to get a miss. You're going to get a miss for this storm. And also this convection permitting model is also for creating a false alarm over this region. So that is what we call the double penalty problem. The convection point-to-point verification doesn't favor a high resolution model. It results in, so that is why we introduce the fractional scale score, where you actually look at a neighborhood size. So if you are looking at this a storm in this red region, then you want to look at a neighborhood, the neighbors around it, to count the fraction of gray boxes that have rain within this region. So now straight to the results. So it's interesting, though, I mean, the top one is what we call the localized fractional scale score, which is the basically fractional scale score variation over space, okay? And then the middle one is the observed GPM. And here is the mean rainfall associated with the tropical African model. And then what you see here is the global model. So you see that the tropical African model in this case, and this comparison is done for the day 2 forecast instead of day 1, because like I mentioned, day 1 forecast is affected by, it's mainly affected by the spin-up problem. And so day 2 forecast is always better than day 1. So you see that the tropical African model, you see that the tropical African model is performing better for most of these regions. So when you do the fractional scale score against the neighborhood sizes for the different regions of study, you see that the scale, the thick continuous line is the tropical African model, and then the broken line is the global model for each of the sub-regions of study. So you see that the tropical African model outperforms the global model for most of the regions apart from the ocean, apart from the Gulf. The possible reason why over the Gulf, the global model is outperforming the tropical African model is because when you do a high resolution simulation, when you look at a convection, what you are doing is you are trying to resolve sub-grid scale features like orography, vegetation, which is actually a feature you see over land and not over the ocean. So the advantage of doing a high resolution simulation is mainly for systems over land where you have a lot of orography and different variation. Over the ocean, everywhere is just plain. So it doesn't favor, really storms over the ocean. That's the reason why performance is better for land storms apart from the storms over the ocean. And this is how it performs for the different seasons. Because of time, I'm not going to talk much about this, but the last part that I want to mention is the variation of the scale for different rainfall intensities. Okay, for different percentiles on the x-axis is an indicative of different rainfall intensities for the different regions. So the top one is the tropical African model. The middle one is the global model. And then the bottom one is the difference between the tropical African model and the global model. Red indicates, red means that, so I want you to just focus on the bottom one. So red means that the tropical African model is performing better than the global model. And then the blue means that the global model is performing better than the tropical African model. So the DJF, you see that the global model outperforms the tropical African model for almost all rainfall intensities. But when you come to regions like the coast and the other areas, you realize that the tropical African model performs better and its scale generally increases for higher rainfall intensities. And it also varies when you look at March, April, May. In June, July, August, we see that for lower rainfall intensities, the tropical African model performs better for most of the regions. But when you come to higher rainfall intensities, the global model is outperforming. But it switches when you come to September, October, November, where the global model performs better for lower intensities, but for higher rainfall intensities, the tropical African model performs better. So when you put the whole seasons together and study for the summary is that for lower intensities, the global model performs better, but for higher rainfall intensities, the tropical African model outperforms the global model. So the conclusions from this work is that West African MCSs are located in regions of strong convergence and high mid-level relative vorticity south of the African jet core. Land MCSs propagate faster, but have lower rainfall rate compared to their oceanic counterparts. A strong vertical wind shear results in large, long-lived, deep storms with high rainfall rates, and also a strong wind shear results in higher cloud top heights relative to their level of neutral buoyancy. The performance of the tropical African model is better for day 2 forecast compared to day 1 due to the long span up associated with the tropical African model. The conversion permitting model performs better at simulating sub-daily rainfall, and mainly because this better simulating sub-daily rainfall and the diurnal cycle, but doesn't show much difference when you do a 24-hour accumulation. So it's very important that forecasters take note of this too. The tropical African model generally outperforms the global model for high rainfall intensities. And that is the conclusion. Thank you so much. I know that there's so much information here, and then you may have a lot of questions. So I will pause here for questions.
Thank you very much, Michael, for this great, explained presentation on atmospheric dynamics in terms of weather formation, more specifically to thunderstorms formation within our. So in fact, thank you for this great presentation. And for our colleagues who are non-meteorologists, because we have heard so much terminologies here that if you don't take time, you will like, what is happening here? But for us, the meteorologists or the atmospheric scientists here, I'm sure we have really enjoyed it because he has really breaking it down for us to know, because there are some challenges that we face when we are using some of these models. Sometimes you could see that, no, this is not reliable to use in your forecast, and the forecaster has to try and look for other models, or even experiences will also count at a point if you are into forecasting. So I think someone posed a question in here that, Maureen, can you really brief me on what is happening here? So SWIFT, we have a project that is ongoing in Africa, that is weather science, weather information in Africa. And the main goal of this project is to improve weather forecasting techniques in the sub-region. So Ghana, Nigeria, Nkrumah, Kenya, Senegal are involved in this project, and our lead partners or donors is from GCRF, which is, and then University of Leeds also in UK, are supporting us in this project. So as a legacy of this project, we brought on board how the things that the research and things that we are finding, how can we communicate this back into the community, and then help people to understand better meteorology and our atmospheric science within the region, as well as forecasting is concerned. So this seminar has come up for us to showcase this information to you. And for today's presentation, our presenter is trying to help us understand in a layman term, is like thunderstorms that are forming over this region on a large scale, how they are formed, how they be able to sustain itself, produce rainfall over us from hours to let's say more than 1 or 2 hours within this sub-region. So that is what he's just helping us to understand. Another aspect to this presentation is, as a forecaster or a meteorologist who uses different types of models, who focus on different types of atmospheric dynamics, so or looking at different parameters to help you come up with this forecast. And we also use satellite informations, we also use model informations. So he's just trying to help us understand what are the dynamics that happens, or even when we are simulating this in model, things that we have to consider, or things that are being considered in modeling. And even these models are being, outputs are being given to us to use. How do they perform? Sometimes you could see that it may mislead you in your forecasting. So that is what he's just trying to put across for us. And he has helped us to get a climatological view of the number of thunderstorms that have tracked over the sub-region, where he divided the region into the Gulf, the SWAP, that's more for the Sahel region, and then we have the Congo side. I think if I get all, yes, that is what he was just trying to help us understand. We could hear words like the convergence systems, the convergence strongly just looking at the conditions that will be favorable for these storms to be able to sustain itself or to develop. And he mentioned something also like the wind shear, which is looking at like the vertical extents, how the clouds will be able to grow. What are the conditions that may affect this cloud, whether it could enhance it or will not enhance it in terms of its development. Those are the things he was putting across understand. And then he also shows us the various regions that were able, like in terms of conditions that will be more favorable for them to be able to sustain on a climatological view. So that means in a day-to-day assessment of these weather conditions over the region, forecasters will be able to appreciate better. I think this were more done on satellite-based and then I think model products. And he also described comparing global model outputs as well as a tropical African model that has been developed also by the UK Met Office with a higher resolution compared to the global model, and he made us understand that the tropical model has a challenge with spin-up time. Spin-up time is just how the model will be able to stabilize and to adjust to have that environment that is simulating, or trying to be able to understand that use information about that area. So it has challenging with Danis, and he showed us that it has a better spin-up time for the second day than the first day. And then the global model is able to simulate for more work best for lower rainfall amount, whilst the tropical or the TAMP model is able to give us a good forecast for a higher precipitation. He pointed out some other things for us to note as forecasters. So in a summary, I think this is what Michael has presented to us, especially for those of us who are not meteorologists here. In a summary, this is what he has presented to us. So it's a great information to enhance our forecasting. And in the long run, good decisions can be made by policymakers and even anyone, farmers, any energy stores in the energy sector, whether the water sector, to help in their plan. Likewise, disaster risk management. This is a great information. I'm going to pause and then open the floor for questions. And I've seen already a hand up by Professor Amekuji. Thank you very much. Professor Amekuji, please, you can go ahead.
Thank you very much, Maureen. Thank you, Michael, for this wonderful presentation and really bringing out a lot of explanations on the concept, really driving the MCS within our region. The striking one for me was, trying to look at the processes in the ocean, and then could you explain what might be the cause why the oceanic, in terms of a time of really dissipation, seem to be far reach in the oceanic process than in the mainland process? That is my first question. And then the second one, I was looking at, if you look at a day forecast, for example, you realize that most of the forecast that is given is mainly 24 hours, but it turned out that the 2-day forecast seem to be performing better in this model. It means that for 1-day model, a daily model, could you suggest a model that is likely to give us a better performance in terms of, do you have any idea on that? Because this one, I'm looking at the second question in terms of GMet's the model choice for Ghana Meteorological Agency. Thank you.
Well, thank you so much, Prof. I'm happy. I'm happy to actually from you today. So I'm just going to start with the second question, which says the reason why we have the day 2 forecast is better than day 1 forecast. And this actually is in relation to the Tropical Africa model. Like I was explaining from the beginning, the Tropical Africa model is a regional model. And so that means that it takes the boundary conditions from the global model before it tries to simulate more realistic storm from the boundary, from the information that it has obtained from the global models at the boundaries. And so it needs to take some time, normally, when you initialize for the model to reach equilibrium, reach reality when you do that initialization. And that is the reason why the spin up becomes, it's longer African model compared to the global model. And then one other reason why the 1800 initialization has a longer spin up compared to the 06 is because at 1800 is just the evening. There is no, if you initialize the model at 1800, there's no insulation. So it will take a longer time for the model to, it basically has to run like the model time 9 times till morning before insulation actually begin to start and before the model's actual storms begin to develop. So it will take a longer time compared to when you initialize a model at 0.6, because if it's initialized at 0.6, then the sun is already beginning to set in. So the model easily adjusts to the real condition, real situation quickly. And that is the reason for this long spin up. And like you have said, if that is the case, then that means that the true forecast is more, is more reliable compared to the one in this case. And this is actually a problem then. So currently, I was at the Met office a couple of weeks ago, and I was interacting with one scientist, the main scientist who is working on this. He's called James Warner. And then he currently, his work is to try to address this spin-up problem by comparing warm start to cold start. So trying to, basically, there's a current work going on at the Met office trying to address this problem and try to reduce the spin-up time so that we can have a more reliable forecast for the day one. So at least if you pick forecasts that were initialized at 0.6, you know that the spin-up time currently is about 12 hours. So after the first 12 hours, every should be okay. So that is, that is what's noting. And the first question, Prof, please, you were asking about the difference between the ocean and the land. I didn't get a question very clearly. If you could repeat it.
So in one of your slides, you showed that the processes for oceanic processes. I think if you can go back to one of the slides where you were comparing the oceanic process and before the forecast. Yes, I think. Oh, go back. I think. Oh, you are moving. Go forward. I think the slide, I could not remember the slide number. Sorry. Go forward. I think you showed the process where you were looking at the process that the MCS build-up processes and dissipation, and then you look at how it's the process in the oceanic conditions. The dissipation is faster than over land. Of course, yes, that's the particular one I would like you to explain.
Okay, so
okay, the MCS participation, that's the one I would like you to explain.
Yeah, so thanks so much. So this is actually describing, we're trying to look at the environment, okay, 2 days before a storm arrives in each of the location.
Hello, Mike.
Yeah, hello.
Your voice is not too clear. If you can quickly check that.
Okay. Is it like it's breaking?
We're having some feedback, I think, from your speaker.
There's a feedback, yeah.
Okay. We'll probably have to.
Yeah. For joining this presentation, and just for record's sake, if you've not entered your name, your institution and country in the chat, please kindly go to the chat right now as we wait some few minutes for Michael to get back to us. Kindly go to the chat, enter your name, the name of your institution, and then your country. Thank you very much.
I've seen the link now, so it should work, I believe, shortly.
Mike, please, have you seen the message?
Yeah.
Yeah, I think your voice is better now. So kindly go ahead.
Okay, so I just want to do the sharing again. I'm sure you can hear me better now. So just share the screen again. Okay, so basically here in this case, we're comparing the conditions, environmental conditions 2 days before a storm arrived to 2 days after the storm arrived. So we have the storm composites, and so it's basically showing what happens over the ocean. You constantly have convergence happening. I mean, you have a lot of winds on the oceans. The winds that come over the land, the monsoon flow that comes over the land that actually introduces moisture onto the land, which eventually results in the storm. They come directly from the ocean. So over the ocean, you always have these winds always over the land. So the convergence is more consistent, but it gets more intense on the day the storm just before the storm is going to arrive. And then when it empties itself, you see that even though it indicates here as blue, which is a convergence, but it's actually a weaker one because the same process that is happening here in the Sahel is also happening here over the ocean, except that it is weaker, a weaker convergence. So basically, the same outflow that you're having here in the Sahel that is resulting in this strong divergence right after the storm has emptied itself is also happening here over the ocean, except that it's not, you don't see it as strong because the ocean is a moisture place which favors the convergence more than, what you have over the land, where you have strong cold pools happening in this region. So in the Sahel side, the outflow from the storm is very strong because you have well-developed MCSs. And so you have associated strong cold pools coming from them. And that is the reason why it is very clear over here, over the land, compared to the oceans. I hope that makes sense.
Hello,
okay.
Prof.
That's okay. That's okay. That's fine.
Thank you very much. So I think I've seen 4 extra hands there. I think before we move to the next, let me just read one chat also from the chat box, which is saying, will you then recommend the global model for marine forecasts and then the term model for forecast over land?
Yeah, I think, yeah, so that's basically the essence of doing this evaluation. We know the strengths of the Tropic Africa model and where it is weaker. So we can clearly see that it is performing better over the ocean compared to the Tropic Africa model. So if I'm a forecaster from this information, anytime I have to do a forecast over the ocean and I compare the global to the Tropic Africa model, I see something in the global that is not the Tropic Africa model, and I have to choose which one to go with. From this information, I'm more likely to go by what the global model is saying than to go by the Tropic Africa model, because you are from this way, you've got to know how the scale varies. Yeah.
Thank you very much for this information. So straightforward, forecasters at least could know which type of model to use at what time and when to use that. Thank you for this feedback. So I'll call on another hand from Jeffrey. Please go ahead with your question. Unmute and go ahead with your question.
Sure, thank you very much. Michael, that was a very great presentation on the, the usefulness of the viewer term model, particularly for, improving forecasts over our region. I just have a quick question on the slide 29, where you show the representativeness of the global model and then also that of the term. Yes, so once you get there, it becomes clear. Yes, so I wanted to find out the conclusion you drew from that. Was it based on the, okay, yeah, so that's based on the fractional scale score, right? And I'm asking this because I would want to know, is it based on the events themselves that you're able to match out that's from the MCSs, or it's the percentiles there are based on the the number of, let's say, detections you made within the grid sizes you allocated? Is it based on the events that you were able to observe? I mean, in terms of
okay, so yeah, so
or it was based on the I mean the grid size or the grid allocations?
The percentile was computed uniquely for, I mean, each of the models. So for each of the model, we computed the threshold of the rainfall amount that should be considered. I mean, so basically for each of the region, we have a look over this region, look over the grid boxes. If the rainfall is above this specific threshold, it's considered as one. It's considered as rain. Okay, but if the rainfall is below that threshold, then that means that we assume it didn't rain. So we have to do this evaluation for different, and that is the percentiles that you see over here. So when you increase the rainfall threshold, then you are trying to only pick out extreme rainfall events. So we computed it uniquely for the global model and uniquely for the tropical Africa model.
Sure. So, and in that case, which one becomes your reference in order to obtain the FSS?
Well, here, in this case, now the reason why we compute it uniquely is so that it's mainly because we know that generally the tropical Africa model overestimates generally it produces high intense rainfall, and the global produce low intense rainfall. So it was necessary to treat them uniquely. And then when we are computing the FSS, we pick
has been rather been used as the reference, isn't it? Looking at, of course, you just possibly you didn't. Yeah, you only look at the difference between the two. But would it have been better if we have a reference? I think it would have been better if a reference is used in relation to the two so that we can really get which of them in this particular case perform better. By just taking the difference, we are only showing the bias. Then I don't know if you can. Sorry for interruption.
Yes. Okay. Sorry, Mike. Can I please go ahead?
Yeah.
Okay. And another question had to also do with you see in the very first question you were addressing, which was on the environment of the MCS. You looked at it within a period. Asking what's the potential for, let's say, going forward, looking at, or what are your plans of variabilities? In fact, now there's a whole lot of issues on climate variability and change components. And so, what would happen if, for instance, there's a strong let's say variability in surface components? Would it still mimic exactly what your findings are, particularly for the one on the environment, the atmospheric environment of the MCS, and then also the wind shear component? Yes.
Yeah, so that is the reason why we didn't pick just a single case to study, because if you just pick a single case in a single year, it's the possibility that that year could have been an extremely wet year is possible. And so that whatever you are saying, something that just happened in a one case and not possibly applicable for all storm types. So to avoid that and to make sure that whatever characteristics and conclusions we are coming out here, they are general characteristics of an MCS, irrespective of season, irrespective of location. That is the reason why we pick the composites of storms. We pick so many storms over the different regions and make sure that the characteristics that we are looking out for is the same. We see the same characteristics in the Congo, in the Sahel, in Southern West Africa for all seasons together. No, it does, irrespective of season, everything we are seeing is what defines a storm environment or what leads to a storm. That is the focus of the study, so that we avoid the influence of, so whether there is an extreme wet year or extreme dry year, we know that once these conditions are met, we expect a storm. I don't know if that makes sense.
Yes, yes, please. Thank you.
Thank you. I think I'll take one chat question before we move. We have just a few minutes more to go. So there's another question from Ikena Orisikawa. Sorry if I don't pronounce your name well. Say, thank you for the presentation. Please, could you explain why the Cape is highest over the SWAL? That's 2940 joule per kilojoule, then than the Sahel, even though they are both continental region, not marine. Also, why do storms affect the SWAL than the Sahel? Thank you.
Okay, so I think that's there's one answer for the two of them. So yeah, the plots that I've shown here, they are a sum of all storms all year round. It is not for all. As shown for, let's say, JJA, you would expect the Cape to be stronger for the Sahel compared to Southern West Africa, because in JJA, the activities are more concentrated in the Sahel. Okay, but this is for all year round. That means that we have Southern West Africa being affected by two periods of intense storm events. In March, April, May, we have a lot of storms in Southern and West Africa. And also in SON, we have a lot of storms in Southern West Africa. So that when you are computing the average, Southern West Africa is going to have more storms compared to the Sahel, which only receives storms only in JJA. I hope that's clear.
So Bashir, please, can you go ahead? I think we have only 2 more questions. I will not be able to pick any other questions after the 3 questions that will come. Thank you.
Okay, thank you for the wonderful presentation. I hope you can hear me.
Yeah.
Please, have you looked at the effects of soil moisture on MCAs? Because there are some work by Doug Parker and his team on the effects of soil moisture on MCS.
Yeah, so I think that, so there are some works that have been done looking at the effects of soil moisture. And then recently, Chris Taylor and Connie Klein are also doing more on it. And they have found out that the storms are more, so mainly convective storms are, the initiation of convective, the preferential location of the initiation of storms is mostly at the boundary between the very wet soil and the dry soil. That is the region where most convective storms are mostly triggered, where you have a very wet period and a very dry period. The storm is more likely to be initiated towards the dry region. It prefers to be initiated towards the dry region rather than the moist region. So that means that if it rains today and there's another storm coming tomorrow, because this soil in this place is wet, but in the nearby region is drier, the storm coming is more likely to move towards the drier region than the wet region. I think that recent work by Chris Taylor has indicated that. I think that work, Connie Klein's work is published already, but Chris Taylor, I think possibly is just about to publish already out. Yeah. I hope that is clear. Is that clear?
Yeah, I think that should be clear for him. So, Mr.
Okay.
Meho,
Just to quickly clarify, is that okay? Just to quickly clarify for Jeff, I mean, what you asked about the threshold for the percentile, the FSS, when we are computing, we create fractions. Okay. So the comparison that we do here, we look at fraction of gray cells that had rain in each of the regions. So we treat each, when you treat each models separately, you do not create any bias in that sense, because you are not looking at the actual rainfall value being compared to, or you are not just subtracting the rainfall value of the observed from the rainfall value of this, but you are looking at the fraction of the gray cells that had rain in model A minus the fraction of gray cells that had rain in the observed. That is what you are looking. You are not looking at the absolute rainfall values. I hope that makes sense.
Yeah.
Okay, Mr. Meho, please can you go ahead? And then the last person will be Professor Lamte. Thank you.
Thank you, Madam Chair, and then good work, Michael. When we were doing a primary or elementary meteorology, we were told that cumulus cloud does not exist in the night just because there's no energy to sustain them. But in your analysis right now, when you were comparing the maritime cape with continental cape, it was clear that even the size of cape over the land does not relate to the amount of rainfall that that comes out of it. But is it possible or supporting, what would be the supporting factor for mesoscale system to sustain throughout the night, and then the following morning they produce heavy rain, if CU cloud does not exist in the night, and which is the cloud which also grow into the CB cloud? I hope
okay, that's yeah, I understand that. So there are different types of. So when you're talking about convective storms, you can have a single cell or a multi-cell storm. So what this study is talking about is focused on MCSs, which is a multi-cell storm. So that means that in a daytime, when you have the sun insolation setting in, you have a lot of energy accumulating, and a lot of energy accumulating from, let's say, from 12 midday towards 6 o'clock. You already have a lot of energy that has been accumulated over the day if you have a very intense sunny day. So by 6 o'clock in the evening, that energy can possibly build up a strong convective system. That's because it is a multi-cell storm. It's a very strong system. It's able to self-sustain itself over the night, because first, it is moving on the energy that has been accumulated over the day, and second, the processes that go on through in a mesoscale convective system actually has a way of self-sustaining the storm. You have an updraft that results in a compensating downdraft. The downdraft, which is supposed to be the outflow from the storm, doesn't happen at the same location. It doesn't happen at the same location of the updraft. So it doesn't kill the storm. So the downdraft is the updraft location. So because it's not happening at the same location, it doesn't kill the storm. The storm lives longer. And the downdraft that is coming out of the storm is able to, it results in cold pools on the surface. And these cold pools, as they flow on the surface, they create that front, because as they are coming out of the storm, the surface has warmer air. So it ends up lifting lifting warmer air ahead of the storm. So that is what we call the secondary initiation. So as the storm is coming, if you study a satellite animation of convective storms, you see that the movement of the storm is not only by advection of the winds, but also the secondary initiation of new cells ahead of the storms is what results in the new cells that develop ahead of the storm, and that keep the storm still strengthened and still moving. So you see that the cell dies, but as the first cell is dying, as it's emptying itself, a new cell is being developed ahead of the storm through the cold pool. And so it's able to self-sustain itself and keep moving, for a very long time. And that's the reason why MCSs can be sustained for a long time. I hope it's clear.
Thank you very much. Thank you very much.
Thank you very much. So I think we'll take the last question from Professor Lamte. We have like 2 minutes more, but last question from Professor Lamte, then this will come to an end.
Okay, Michael, congratulations. Very good job done. And I like the way you link your results to operations. It shows that you were actually from Ghana Meteor. That's good. I have a question. Sorry if I missed something, but you have categorized, you were tracking storms and you have categorized them into land and oceanic-based and land-based storms, right? My question is, you know that some of the MCSs develop on land, but they propagate to become hurricanes in the Western Atlantic. Did you by any chance look at this property? Because I think that you are, the way you are studying the environment of the storms, if we can identify which of the MCSs that generate on land and the unique environment associated with it actually propagate and eventually become a hurricane in the West Atlantic, I think it will be an interesting thing. And my second question is, if you've done so, have you observed anything about latitude 8 degrees north and latitude 12 degrees north? There's some hypothesis that some of them, the storms dissipate and the other one, the storms actually meet the conditions suitable for the cyclogenesis in the ocean. Thank you.
Okay, yeah, thanks so much, Prof. So just like you are saying, I did, which I didn't show here, was to look at the association of the storms with the Africa Easterly wave. I noticed that some of the storms live longer, long-lived storms. It could live for many days, even up to 4 days. And those very longer-lived storms were living longer because they were associated with the African Easterly wave. So if you have storms that are initiated at the far right of West Africa, let's say the Congo area, and it finds itself within the trough of the wave, it is able to keep itself sustained across the whole land region. And by the time it's leaving the coast of West Africa, the Senegal area, it has accumulated a lot of energy from the land. And by the time it enters the ocean, because there's a lot of abundance of moisture, that is how come some of these storms become so strong and are able to sustain themselves over the ocean and then result in a hurricane. So some of those results there, but I didn't go into further details to do further analysis on most of these those storms. So like you were saying, there's the northerly track of the African Easterly wave and the southerly track, and which one of them really sustains hurricanes. I have not yet done that. They actually students here who are focusing more on the hurricanes. So hopefully, I'm sure that those findings will be known. Yeah.
Okay, thank you.
All right, thank you very much, Michael, for answering all the questions, and thanks to all our participants for your great questions. And thanks to everyone who made it to today's session. I think there was one recommendation from Mensa Atakura, who is saying that GMA, actually we are GMet, that is capital G, capital M, small e, small t. So that is our abbreviation for Ghana Meteorological Agency. So she's recommending that if you could organize frequent training via Zoom or face-to-face for broadcasters who present weather reports and those who want to present reports. Most radio, TV shows presenters don't present weather reports over lack of knowledge. So your recommendation is well noted, and then we will try and then work around that. So thank you all for joining for today's session. This is a monthly thing we do. We break for some time because we're having other activities, but we are hopeful to be resumed, and then next month we'll come up with another interesting presentation. So we look forward to seeing you all. Kindly share with anybody when you receive our links for this invitation. So on this note, I would like to wish everybody Merry Christmas, and then we'll meet you next year. So I think we'll just take a group photograph. If you can all turn on your camera. we will take a group photograph before we leave. Thank you all for coming. I'm very grateful for this presentation. So our photographer, please, we are ready. Please, just a second, the photographer is trying to.
Bashiru, your hand should come down. Ah.
Okay, they are taking the last one, and you're almost done. All right, thank you so much, and thanks to our photographer for
thank
the
you all.
pictures. So, Merry Christmas and a Happy New Year in advance. See you all next year. Bye-bye.
Bye.
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 Bye. Sabi, you have looked at my ceiling again. Sabi,